So we are set up now to collect data using Vermeer's Go Direct colorimeter. And basically, as you can see, there are different LEDs that you can choose. We have the 470 nanometers, which is going to give us the blue light passing through it. And we can also calibrate this. You slide open the chamber, and to calibrate it, you put in a blank, which is basically just a cuvette that has distilled water, because we're trying to set it to a 0 point where it's not actually going to absorb anything in that process. We press the cowl button, and what it will do is it will zero it and set it so that the plastic and also the water itself is not absorbing any of the radiation that you're going to be working with. When we look at the graphical analysis app, we are now ready to start collecting data. And what we would do is we would begin with the most dilute solution first, which is test tube number 1, which had only 2 milliliters of the FeSCN with 5 milliliters of the iron. Make sure I close that up. And let's take a look at the graphical analysis app to allow us to be able to work with this. So right now we're looking at an absorbance value down in the bottom corner here, which is showing me about 0.26, 0.27. I have this set up so that it's going to collect data. And when I hit the keep button, it's going to ask me, what trial is that? So I'm going to put down that it's test tube number 1. You'll notice it tells you the absorbance is 0.27, but it also gives you the percent transmittance, which your teacher might want to talk to you a little bit about how percent transmittance and absorbance are related to each other. Now, in normal situations, what you would do is take the same cuvette, you'd rinse it out, you then go and take another solution and put the next one that you'd have in there. So I'm going to use test tube number 2. So usually rinse the cuvette with that next solution, and then you put that back inside the colorimeter. So I'm following the same setup. Now in the bottom right-hand corner, the absorbance you will see is at about 0.42. So that's test tube number 2. So I'm going to hit keep and enter that I'm looking at number 2 for my point. And the transmittance, because the absorbance is greater, that means the transmittance of light going through it is less. So I'm going to keep that particular point. And let's take a look at number 3. Test tube number 3 has 4 milliliters of the FeSCN with 1 milliliter water and 5 milliliters of the iron. So it's getting more concentrated. And now my absorbance is following the path that as the higher the concentration, you're getting a greater value of absorbance. So we're at about 0.57. Let me keep that one. Make that value as my third trial. And keep that point. And I have one more of these mixtures that we've made. And that's the last one, which is 5 milliliters of the FeSCN, 5 milliliters that you have of the iron, and no extra water being added to it. The first 3 were in a situation where iron was an excess and the FeSCN was a limiting factor. In this case, they're combining in a 1-to-1 ratio, so they should all be consumed, except for some of it that's reversing from the complex FeSCN breaking back apart. So we're at about 0.79. Let me keep that last trial of the ones that are the unknowns, and that would be number 4. So you can see that it's a fairly linear relationship, because as the concentration increases, so does the absorbance. That's what Beer's law is. Our final one that we want to do is now take a look at the one that had the standard, the one that had the mixture of 0.2 molar of the iron with 0.002 molar of the FeSCN. What happened in that case is that we've used up almost all of the FeSCN and converted it over to the product. So if I keep that last one and record that as trial number 5 for test tube number 5. Okay, so let me keep that last one, number 5. So we now have your data that you could use for your analysis of your individual substances and go from there. Since we are trying to look at what the concentration is based on taking a look at just the absorbance, we're going to compare the one where we know the standard that has used up all of the FeSCN. We're going to use that to be able to compare to the amount of the others about how much of the FeSCN was actually bound on to the iron and what the net ratio is between those. So let me stop this data, and I'm going to save this so that we could use this for experimentation later on. So this is the KC of FeSCN experiment. And I'll put in that we use the colorimeter for that setup. And I'll save this and share this with you later on with your teacher so you have some data that you can look at and go through your analysis. The rest of the experiment at this particular point is going to be based on taking a look at analyzing your results, trying to figure out what the changes are between those results, and being able to do the analysis from those by comparing what happened to the original concentration, what's the change that had to occur to end up forming your new absorbance, and then be able to figure out what the situation is for your final product. This is going to involve doing what's called the Rice chart calculations. Your teacher will talk about this in more detail with you. Briefly, what the Rice chart is that you are taking a look at what's the initial reaction that's going on in terms of the process, what's the change that occurs between those, and then what's the equilibrium concentrations that you have, and you're able to work those out and solve for what the equilibrium concentrations would be of each one. So when you look at the processing data section of this lab, you'll see that in order to find the initial concentrations of both the iron 3 and the FeSCN minus, what you have to do is take the number of milliliters that you used of each one of those solutions and then divide it by the total milliliters of the mixture. So in all of the test tubes, the total volume that you used was 10 milliliters. For the iron, it was 5 milliliters in all 4 of the first test tubes. So 5 out of 10 times the initial concentration, they were 0.002 molar solutions, that would give you that value. For the FeSCN, that's going to vary because we've used 2, 3, 4, and 5 milliliters. So it'll be the volume of the KFCN that you had, again, divided by the total volume of 10 milliliters times its concentration, 0.002. Those would be your initial values. To figure out what would be the value at the equilibrium of the FeSCN, it's based on the absorption of the equilibrium solution relative to the absorption of the standard solution. The standard, again, being the one that had the 18 milliliters of 0.2 molar iron and 2 milliliters of 0.002 molar of the KFCN. What's happening here is that you are basically taking that 2 milliliters of KFCN and you're diluting it to 20 milliliters of total volume. And then its concentration was originally 0.002 molar. So that is going to be completely consumed to form that standard by mixing with the excess of the iron that we added to it. So that would give you the amount of the equilibrium of the FeSCN. To then get the equilibrium of the iron or the thiocyanate FeSCN minus. What you do is you take your initial concentration and then minus the equilibrium concentration of the complex that was formed, the FeSCN2 plus. To get the K value, again, it's always looking at the concentration of the products that you formed in the reaction, raised to a power based on how many moles in the balanced equation, divided by the product, divided by the multiplication of the concentrations of the two reactants, each one of those raised to the power of the moles that were in the equation. And in the balanced reaction, it's all 1 mole of everything combining together. So 1 mole of iron 3, 1 mole of FeSCN minus, 1 mole of the complex. This will give you your K values. Since you did 4 different trials, you can compare and see what the average is. And typically, we're going to be looking for something around, 140 to 170 as normal. The more accurately you measure your solutions, the better your results usually are. So you can be a little fussier with your measurements using maybe a pipette that can be more accurate than a graduated cylinder. If you have any that look like they're out of place or you end up somehow getting negative concentrations, you must be dividing and subtracting by the wrong numbers in your setup. So there's the lab. Good luck to you in terms of your analysis and trying to figure out the relationships that occur, and have a great day.